Hello everyone, welcome back to our channel. In this video, we'll be discussing about the last problem of today's weekly contest, number of good paths. The problem states that you are given a tree and each node of the tree has a value associated with it. Now, you need to count the number of good paths in the tree. Now, what is a good path? Good path is a path which satisfies these two conditions. The first condition is starting node and the ending node value should be the same. Second, all the nodes between the starting nodes and ending node should have value less than or equals to every other node. Okay, so basically, the starting node or the ending node value should be the largest value in this path. Okay, so let's take an example. Let's say uh, we we have this tree and the inner ones, ignore the inner ones because those are the indices. The outer one are the values. Okay, now if you take this path 4201, this path this path is actually a good path because it starts with 3 and ends with 3, right? And every other node here has value less than or equals to 3. So you can see 2 and 1 are less than or equals to 3. So this path is a good path. Now let's take this example 320. This is not a good path. Even though this starts with 1 and ends with 1, every node here is not less than or equals to the starting node. Basically, this 2 is not less than or equals to 1. Hence, this 1320 is not a good path. So you need to you need to count all the good paths in the given tree. Okay, now let's see how to solve this. First of all, let's talk about what is the simplest thing to count first. So the simplest thing is so we have to find out, like we have to satisfy this second condition, right? The first condition is very simple. The starting node and ending node should have the same value. So this is very simple. We can do it through a lot of different ways. The second condition says that all the nodes between the starting node and ending node should have value less than or equals to the starting node. Okay, so this condition is a little bit tricky. So how can you skip this condition, or how can you make sure that this condition is automatically satisfied? One way is to start with the largest value, right? If you have the largest value and you take any path, so your starting node is the largest value and you take any path, that path should be a good path because every node there is should be smaller than or should be less than or equals to the starting node, because starting node is the largest value. So in this example, what I've done, like the outer one, you can ignore the outer ones. Outer ones are not are the indices. The inner ones are the values. So we care about the inner ones. Okay. So now what we have discussed that if we start with the largest node or the largest value, then any path that we consider which start and end with the largest value will be a good path. So for example, if you consider this path that starts with this and ends with this will be a good path. Okay, so why this will be a good path? Because it starts with 7, which is the largest among all the values here, and it's in with 7, and because it is the largest value, this everything here should be smaller than or equals to 7. So that so this path is a good path. So we counted that. Now what about the other values? So we know that we can now calculate. So let's say there are x number of occurrences of 7. Okay, so now if there are x occurrences of 7 in this tree, what is the number of path? Number of path would be xc2, because you can take any two nodes of among this 7 nodes, among these x nodes, and there will be a path because this is a tree, everything is connected. So there will be a path. So total number of nodes or total number of paths, good path that you found out initially is xc2, where x is the count of 7 or count of the largest value in the tree. So once you have found this, the largest path, the path which consists of largest value, how to calculate other paths? So let's see. Now, if you are taking any other node, that node is less than 7, then you have to take care of the second condition, because second condition will not be automatically satisfied. So what can you do to make it satisfy? The simplest thing you can do is to remove the node altogether. Let's say this node doesn't exist. Okay, and similarly this node doesn't exist. Now if this node doesn't exist, these two edges will also not exist. Okay, and now you say what you can do. Basically, apply the same logic. Now you find out the largest value in this tree. What is the largest value? 5, right? Now take out fives, and that any path forming fives will be will be a good path. Why? Because 5 is the largest now. You have removed everything less greater than 5. So now let's see one path. Let's take this path. Okay, so this is a good path. Similarly, if you take another path like this is also a good path. And same goes for this. This is also a good path. So basically, now what you have done is you have simply removed the largest value, and now you have applied the same algorithm again. Okay. Now there is a catch here. This path will not be a good path because this is not a path at all, because this edges are now removed. So as and when you are removing things, you have to make sure, or you have to take care how many count of nodes are there which have the same values and which are connected as well. Second condition comes which are connected as well. So in this case, there are two components. One component is this entire piece, okay, and second component consists of this piece. So in the first component, there are three nodes which have value 5, and in the second component, there are one node which have value 5. So now, if you have to find out the total count of path, you have to take this component separately and this component separately. So what do you mean by separately? Basically, you can take any two nodes from these three nodes, and you can take any two nodes from this one node. So now again, you will apply the same formula 3C2, which is basically 3 into 3 minus 1 by 2, which will give you the number of paths which are good in the first component, and similarly for second component, as there is only one node, there is no path possible, so this contribution will be 0. So hope you get the intuition what we are doing here. Okay, so now let's take one more example, and let's say now you have to find the next value, or the next good paths. So remove 5 because you have taken care of all the fives already, so remove all the fives. Now here again, there are two components formed. One component which consists of this, and second component which consists of this. Okay. Now in the first component, you count out the largest value, which largest value is 4 now, right? So in the first component, the number of count of force is 1. Second component, count of 4 is 0. So basically, there is no good path which starts and ends with 4, because from 1 you can't select two nodes, and from 0 also you can't select two nodes. So that like 4 we have done, and if now we will remove 4, and there is only one component, and in one component this 3 occurs two times. So there will be one possible path, and that possible path is this. Okay, so hope you get the idea. Now if we have to implement the same, what would be like what it would look like? So we what we are counting a number of nodes with a particular value. So that is simple. We can do it using a lot of different techniques. Second, what we are doing is we are removing nodes and edges, right? We are removing nodes and edges, and we have to find out, or we have to keep track of connected components as well. And secondly, we have to find out the count in those connected components. So that is difficult. You can do it by like creating a altogether new by treating it as an altogether new graph and just doing a BFS or DFS starting from the starting node, and that would actually solve this, but that would require you to iterate over the entire thing once. So that would require order and time, right? So every time you are removing some node, you are recalculating your entire component, and that would require order and time. So in total, you will be doing this for n number of nodes. So total, you will be doing this for all the nodes, and complexity would become order n square, which is not sufficient here because n is of the value 10 to the power 4, 3 into 10 to the power 4. So what exactly we can do now? The thing is, we can't tear apart the nodes, but can we do stitching of the nodes efficiently? The answer is yes. We know of a data structure that can stitch nodes very easily and also keep track of connected components. The data structure is DSU. So now, what if we apply the same logic but in reverse order? And we can see that would actually fit in nicely, and because of DSU we can implement it faster than order n square. Basically the stitching will not take more than order one time, so in total this second n would be gone and our complexity would be order n. So that is the idea. Now how to, like, let's look at how to solve this. So first of all we need to stitch things, right? So let's go back to the graph again. So we have to stitch things. So what we are doing is, what we are saying is, there is no edges at all in the initial go, and we will be stitching things. So now let's say when we say that okay, I have to find out, I have to stitch everything with 5. So you have to be aware of the adjacent nodes of 5. So basically the thing is, you are given, like in the problem we are given the edges, uh, like we are given the edges 0 1 0 2 0 3 2 3, but when we are stitching things we will be visiting all the neighbors of a particular node at once. So basically we need adjacency list. So we'll prepare the adjacency list with beforehand, and now we are ready to see how we can apply the same algorithm but in reverse order, and we can see how DSU fits in nicely there and reduce the time complexity. So this is exactly the same graph. What I've done, I've just noted down the adjacency lists here, and I have removed all the edges. So now what we have to do is we have to start from the very bottom. So what is the smallest node? 1, right? So what I've done is I've created a map as well for all the values. So we have 5 different values here, 1, 3, 4, 5, 7. So what I've done, I've created a map which says for 1 how many nodes are there. So for 1 exists in 0 and 6, so that we can easily say what nodes to work on in in at any given point of time. So starting from 1, like we have the smallest node as 1. So initially everything is by itself. So every node is a good node, or every node, like starting from, if you start from 7 and end at 7, that is a good node. So initially we will add n to our answer, so that is okay. Now we have to find out nodes which doesn't start and end at the same node, or we have to count the path which doesn't start and end at the same node. So let's start with 1. So how 1, like you have 0 and 6 here. So you activate 0 and 6, everything is deactivated, let's call that deactivated. So now you activate 0 and you activated 6. Now once you activated 0 and 6, you can actually connect or connect everything starting from 0 or starting from 6. So basically you can connect every node from 0 and 6, but those nodes should also be active. So now you can see from 0 we have 145, 145, but none of 145 is active, so we will not connect anything. Now from 6 you have 4 and 8, so 4 and 8, again not neither 4 nor 8 is active, so we will not do anything. So now we will ask DSU who is the who is the leader of 0. So I am assuming that you know what DSU does. So we have a leader concept there. So what, like we have used the same technique previously as well. We will come to that. But what is the leader of 0? So leader of 0 would be 0, right? Because that's the only node in this connected component. What is the leader of 6? Leader of 6 would be 6 only, because that is the only node in this connected component. Now what you will do, you will see how many of them have the same leader. If they have the same leader, it means they belong to the same component. Does it make sense? So we'll look at an example soon, but here they belong to different leaders. So for leader 0 there is one node which have count 1. For leader 6 there is one node which have count 1, which have value 1. So from one node you pick two node, it is not possible. From one node you pick two node, it is not possible. So that's why this is not possible. Like you will not get any good path from here. Now let's talk about the second. Okay, so we are now introducing three. So notice that we are only at any given point of time, we are only dealing with maximums because other nodes are inactive, right? So now once you introduce 3, 4 and 8 becomes active. Okay, so let's make them active. So 4 is active, and similarly 8 is also active. So now if these two are active, so once this 3 is active, so like once this force is fully active, then you go to 4, you see that it has adjacency list of 0 and 6. So 0 is also active, so let's connect this. Okay, and similarly 6 is also active, let's connect this. Now you just now activated 8 as well, so you will go to 8, the adjacency is 6, 6 is again active, so you just connect this. So uh, once you have these things, now you say what is the what is the leader of 4. So leader of 4, if you look at leader of 4, it will be one of these nodes, right? Let's say 0. This belongs to one component, so let's say 0 is the leader. So leader of 4 is 0. What is leader of 8? 8 also belongs to the same component, so leader of 8 will be 0. Okay, now once you done this, you know that there are two nodes which have leader 0, right? So it means that there is a component which have two nodes which have value 3. So in that will form a single path, like 2c2, like this will contribute 2c2 to our answer, that is 1. So our answer will be increased by 1. So where, like, you can see also, this is the path that we are talking about, that starts with 3 and ends with 3. Okay, now we have taken care of these things. Okay, now let's move forward with 4. We will take one more example, and that we will conclude there. So 4, again, like 4 is not that interesting, because 4, if you activate 4 here, you will see that adjacent of 4, sorry, you will activate 3 here, and now if you can see that adjacency of 3 is 1, which is not active, so this will not do anything. And now again, if you find out the leader of 3, leader of 3 would be 3 only, because that is the only node in the connected component, so you can't do anything. Okay, now let's just talk about 5. So this is interesting. Now it activates 1 2 5 9. Let's activate them. 5 is activated. Okay, 9 is activated, 1 is activated, and 2 is activated. Okay, so now if you look at the, like, if you just perform the same operation, like, because they are activated, they might have been connected to some other nodes. So if you look at the 5 has 0 and 7, so let's connect it to 0, because 0 is activated already. 7 is not activated, so we will not connect this node. Now second is 9, so 9 is connected to 7, 7 is not activated, so this is also not required. Now let's look at 2. 2 has 1 and 10, 10 is not activated, but 1 is activated, so let's connect this. Let's look at 1. 1 has 0 2 3, so 0 is activated, so let's connect this. 2 is already connected, and let's connect 3 as well. So now you can see this entire thing comes to one component. So if you ask the leader of any of these nodes, you will get single value. Let's assume it is 0, and this belongs to second component. And if you ask the leader of this, you will get 9. So let's do the same thing. What is the leader of 1? 0. Let's assume 0, because it belongs to the same component. Leader of 2, again it will 0. Leader of 5, it will be 0. And leader of 9, leader of 9 would be 9, because 9 belongs to single component. Okay, so now there are three nodes which have value 0 or leader 0. So basically what you get from here is there are three nodes which have value 5, and you can select that belongs to a single component because they have the same leader. So now you calculate 3c2, which is 3, and this will contribute 3 to our answer. Now this is for the one component which has leader 0. Second component has leader 9, but now if you look at leader 9, there is only one node, right? Because count of 9 is 1. So because there is one node only, this will not contribute anything. So this will not contribute anything to our answer. So this is how we are doing it. So hope you get the intuition. So what we have started with saying that we will start with the largest value and we will keep on removing the largest values. And we saw that we can't do it efficiently without iterating over the entire tree once. So what we have done is we have used the opposite way. We start with nothing and we keep on joining things. And because joining things is something that DSU provides very efficiently, we can actually we can actually use DSU to maintain what is the connected components. So now how we can use the connected components, we will ask the leader of every nodes here and just count how many of them have the same leader, and that will be the count of number of nodes in that connected component. So hope this entire solution is clear. Let's look at the code that makes things little bit more clear. So what we have done, we have okay, so first DSU, I assume that you know DSU. So it has two function, finding out the leader of a node and just merging two nodes. So I am I'm assuming that this is already known. Now second thing is what we have done, we have prepared the adjacency list. So this is also very simple. Let's forget about this. So the third thing, if you remember, we have calculated this map as well because we need to know which all values or which all nodes have the same values so that we can apply the formula on that particular node. So basically this we need because starting and ending node should be similar. So this is something we need. So we calculated this map as well. Okay. Now what we have done, we are iterating over each of this array. Okay. So now for each array, what we have done, we have activated that node and we have also connected it with the children. So we are iterating over the children of this node, and if the children is active, we are connecting them. Okay. So now after this, we have all the connected components with us. Now only thing that remains is we have to count how many fives are there in each of these connected components. So that's what we are doing with leaders. We are finding out the leader of uh, every node here. So we ask DSU to give us the leader of every node. Now we sort the leaders. Now we just count how many of them have the same leader, because if they have same leader, it means they belong to the same component. So we just count how many of them have the same leader, and let's say that this is coming in the count. So you will just do count into count minus 1 by 2, because that is the count C2 basically. So now once you have done this you will add this to our result, and that will be the answer. So hope you got the solution, and hope you also understand how to reach this particular solution if comes in future. Basically, wherever you see that you are tearing apart things and you need to fast this thing up, you can apply the reverse algorithm. We have done exactly the same thing in one of the past lead code hard problem in weekly contests. I will link that video in the description below. Make sure to check it out. It will also teach you the same concept, and you can actually visualize it how where and all you can apply the same concept again. If you like the video, give it a thumbs up and do subscribe to the channel if you haven't already. So liking the video and subscribing actually help me keep motivated, because I see according to YouTube stats, 90% of them, 90% of you doesn't subscribe, but you like the video. So make sure to hit the subscribe. So I will see you in the next one. Thank you.